Let us see this configuration. This configuration is called as scratch drive actuator, inchworm like walking sequence. So, in this actuator, so we will be having a left clamp, and a then there is a plate, and this is a kind of a arrangement which is available. So, what happens is, because of these kind of it basically used in the kind of a MEMS technology with micro robotic applications, by giving a kind of an actuation to it. So, when we try to find an electrostatic charge in this, this will create a kind of an inchworm mechanism over here. So, this inchworm mechanism or this inchworm displacement will be in the order of few microns. So, this is one configuration. Apart from this, these kind of actuators, electrostatic actuators, has a potential application or a potential flexibility in developing in the form of a rotary based system. Let us see some kind of rotary based electrostatic actuators. So, top drive electrostatic rotary actuator, rotary actuator with ring shaped bearing. So, in this particular case, we will be having a kind of a stator configuration. Over the stator configuration, there will be a kind of a over the stator configuration, we will be having a kind of a dielectric material. This is a stator, a dielectric material. Then there will be a kind of a slip ring arrangements, and then there will be a rotor ground. So what happens is, in this overall configuration, since it gets actuated because of the electrostatic charge, different slots are being entangled in this particular system. So in these slots, so what happens is, each and every slots are energized in such a way that this will result in the rotation of the dielectric material, and the slip rings which is available will be used for appropriate manipulation or appropriate control over the rotation, and then there will be a rotary ground which will be available. So these kind of rotary actuators, so in the earlier cases we have seen certain amount of linear actuators. So these electrostatic actuators are now configured also in the form of a rotary actuator. In addition to this, so this configuration can be extended in the form of a linear slider and a stator. These linear sliders will be integrated with interdigitated structures appropriately, and these sliders will also be integrated with interdigitated structures. So what happens is, these linear sliders and these stators will be coupled in such a way that whenever there is a kind of a linear motion persists, then this will result in a kind of a actuation. So in fact this is a kind of a configuration. So you can refer it is called as two-phase resonant electrostatic so these two four-phase resonant electrostatic motors will be helpful for us for a kind of a linear arrangement, where it can be used for converting a kind of a linear actuation in the form of a in a linear fashion. Okay, so overall if you try to look into it, so these configurations are well established based on the types of modes which is being reported, and based on the modes appropriately these kind of electrostatic actuators are being developed. However, we have not touched upon the comb drive actuator, so there is a separate section on the comb drive actuator which we will be discussing. Now let us discuss about the other set of electrostatic actuators which are commercially used. One such electrostatic actuator is called as a electrostatic foil actuator. So as far as in this electrostatic foil actuator is concerned, so if we closely observe the overall configuration of it, so it's a kind of a wall where there is a flexible conductive film which is available, and there are two insulating layers. When a voltage is applied appropriately, this flexible conducting film will try to take a shape in such a way that this will be helpful for opening and closing of the wall. So ideally the actuator consists of two silicon electrodes forming a chamber. Between the electrode, a metallic foil a foil made of steel or FeNi alloy is placed. So this foil is formed into an S-bend which can travel from one end of the chamber to the other end. For operation perspective point of view, a voltage is applied either between the upper electrode and the foil of the lower electrode, so that these foils can be appropriately actuated to get a required displacement what we are working upon. So as far as in this electrostatic foil actuator is concerned, the electrostatic foil is pulled towards the respective electrode by an electrostatic force with S-like bend traveling through a chamber. The large displacement can be achieved by increasing the volume between the electrodes, and mechanical can also be used to valve the control of the flow gases. So, the larger displacement can be achieved by increasing the volume between the electrodes, and the mechanism can also be used as a valve to control the flow of the gas. So, the gas inlets open into the space between the electrodes, and the two outlets are formed by the recess in the electrode. As the foil bend travels along the inside of the wall, it opens up a path for the gas on one side of the chamber and close it on the other side of the chamber. So, this is a kind of an biasing which is being applied over here, since it is a kind of an S-bend based electrode which is mentioned over here. This S-bend based electrode will take an appropriate shape to have a control over the wall which exhibits over here. So, ideally what happens is, so there are upper electrodes are there and the lower electrodes are there, and then there is a spacer which is available. So, by configuring this voltage, so appropriately we can have a kind of a construction. Okay. So, this is a kind of an application, like in this particular case, if you closely observe, the overall S-bend kind of structure is a kind of a thin foil based structure, and these thin foil based structures are capable enough in such a way that when we try to deflect it, so it can it doesn't requires any kind of load. However, it acts as a kind of a cantilever based walls or a kind of a deflection based walls, so that these deflection based walls will deflect and appropriately gives a direction to the requirements. Now, let us discuss about an electrostatic micropositioner, so which is considered to be one of the key device with reference to functional perspective point of view. As far as these micropositioners are concerned, so these micropositioners are used in a kind of a optical communication. So, it is something like this, like these micropositioners are meant for holding the optical fiber, especially during the optical communication network, so that the deflection, or if we need to have a kind of a micromanipulation, that can be established using an electrostatic actuator, and appropriately the optical fiber deflects, and then it will be helpful for manipulating the connection. So, as far as this optical communication networks and optical computers needs a flexible optical coupling and interfacing techniques, here a very high precision is required to align and connecting the optical fibers. Even the smallest deviation can lead to an excessive light attenuation. So, the whole device consists of two parts, the micropositioners and a stationary part with an integrated optical channel, and if it is the task of the micropositioner to align the fiber with their corresponding channels. Now, as far as in this electrostatic micropositioner is concerned, so the micropositioner has a base containing of several V-shaped grooves into which the optical fiber needs to be aligned and placed. Now, along with the V grooves, there are different actuating electrodes are also available, and the optical fiber is coated with a thin conducting film with an insulating layer. So, the groove itself has a wider part and a narrow part, and the wider part there are alignment electrodes on either side. The optical fibers are coated with a thin metallic layer so that they can be actuated electrostatically. Okay. So, the coating can be either through a kind of a sputtering, or it can be through a kind of a thermal evaporation. So, if an electric voltage is applied across one of the electrode, the fiber is attracted by this electrode. Therefore, by controlling the voltage of both the electrodes, the fiber can be exactly aligned, and the metal layer of the optical fiber is applied by a sputtering process, and the groove is produced by a bulk micromachining technique on a silicon substrate. So, the smallest distance between the optical fiber and the electrode is 50 to 30 ttm, and the electrodes were produced by depositing a thin aluminum layer with a kind of a lift-off technique. So, this is a kind of an electrostatic positioner. Of course, there are other configurations of electrostatic positioners which, like these are some kind of slightly on above the microns level. However, if we need to have a control over a higher order micron level, then electrostatic based comb drive actuators are considered to be one of the potential. However, electrostatic based comb based actuators are deployed for different other functional related applications. Okay, so just to summarize, so ideally in this particular module, so we had discussed about the three different types of actuations, like so especially the micro actuation and so we have taken this electromagnetic actuator, we have discussed the fundamentals behind this electromagnetic actuator, the overall applications. So we have discussed about the different types of magnetic property which can be efficiently used for micro actuation. So we started with dimagnetism, we had discussed about paramagnetism, we had discussed about this ferromagnetism and ferrimagnetism based structures, antimagnetism. So in the case of a dimagnetism, how these structures are deployed, and in the case of paramagnetism, what are the different applications of the paramagnetism, what is the overall XR range for a paramagnetism which can be appropriately quantified. So we also had a discussion about this ferromagnetic structures, about an antiferromagnetic structures, ferrimagnetic structures, a Lorentz force actuator which is being efficiently used over here to take care of the flow inlet, and overall process parameters which are involved for the same. So we have taken a small case study where that's a kind of a middle ear implant hearing device. So using this middle ear implant hearing device, we can see how the structures are implanted and how the actuations are being taken care, and an oval window and an inner ear, this one. And then we also have a magnetic micro actuator with a planar coil, so where there are some spring arms which are available, and this spring arm will take care of the movement of the structure. Then we also discuss about the varying configuration of these magnetic structures, where these magnetic structures are deployed in any kind of structures using a kind of a active coating. In certain cases, these magnetic segments are integrated with the structures. In certain cases, magnetic particles are being dispersed in the structures. Now, as far as magnetic film is concerned, since we are already well versed with the microfabrication techniques, so with reference to the microfabrication, so we have a E-beam and a physical vapor deposition or dip coating which is available, and then there are different magnetic segments which are being deployed over here, like electro deposition and oblique angle depositions are there. And with reference to micromanipulation technique for actuation, there are different designs which exhibits. So the magnetic micromanipulation is concerned, so we can classify based on the functionality with reference to torque actuated and force actuated. In the case of torque actuated, we have a time varying magnetic field. In the case of force actuated, we have a inhomogeneous magnetic fluid. And in the case of time varying magnetic field, we can classify as rotation, oscillation and stepping. In the case of inhomogeneous, so there are particles which are being available, and based on these particles we can do the manipulation. And then we had discussed about this origami based magnetic actuator for micro robotic application. These are kind of a flexible origami based actuators, and these magnetic particles are integrated with the hydrogel, and they are appropriately programmed in such a way that, so whenever there is an actuation is there, so there is an appropriate deflection which exhibits in this system. So this structure can take up any shape based on its capability. And then in the case of a magnetic actuator, these magnetic micro actuators based robots has a potential application in different biomedical related aspects. In fact, this complete picture will give you a clarity in what are the different nodes or the different applications these magnetic based actuators are deployed, and how it has an impact towards the characteristics. Then we also had some discussion about this magnetic and magnetostructive based structures. Then with reference to piezo is concerned, we had discussed about a piezoelectric effect, the overall configuration of a piezoelectric effect, how a mechanical deformation has an impact on the piezoelectric effect, and the electrical displacement has an impact on the piezoelectric, the generalized 3D space formulation of a kind of a piezoelectric impact, and the constitutive equation for the piezoelectric actuation. And then we also had a discussion about this configuration related to short circuit and an open circuit system, and then a piezoelectric actuation, like the importance of the polling, how these polling will have an impact with reference to the functionality, improving the functionality of the structure. So we also had a discussion about how the performance of a piezoelectric actuation is studied with reference to strain and curve, and then we had a discussion about hysteresis, about the amplification factor. So some of the key elements, which includes micromembrane pump, micro valves, then chopstick grippers, which is used for a kind of a micromanipulation, has been discussed, and the piezoelectric actuator used for a kind of optomechatronic application has been discussed over here. So this is highly useful for kind of a dynamic loading and unloading. So this is a kind of a piezoelectric based manipulation. So we have a kind of a piezoelectric beam based on the movement of the beam. So we can have a kind of a vibration, and through this vibration, so there is a kind of a displacement which passes. So this displacement has a direct relevance towards the frequency. So what we did is we had two different configuration. One is a frequency based, another one is a micro displacement phase for micro manipulation. So we also had a discussion about electrostatic actuator, the different configurations of electrostatic actuator, a vertical actuator with a parallel plate, then a linear actuator with a lateral actuator with a parallel plate. We had a discussion about this scratch drive actuators, about the different operation modes of an electrostatic actuators, and the different types of electrostatic actuators which are being integrated in a customized system. So one is a kind of multiple degree freedom of electrostatic actuators, a perforated intermediate electrostatic actuators, bending plate actuator configuration, a scratch drive actuator which inchworm like walking sequence. Then there is a top drive actuator, and then there is a linear slider based actuator which exists. And then we also had a discussion about this electrostatic foil actuator, which is used a kind of a wall based system. And then we also had a discussion about the configuration of an electrostatic micropositioner and the application of this micropositioner in optical communication related applications. These are some of the references. So I urge you to go through this YouTube video, so you will have a better clarity on the magnetic based actuator for micro robotic related applications. So there are wide varieties of micro actuators are there, which we have seen with reference to different functionality. Like in fact, shape memory alloys are used, micromotors are there. Now, like overall, if we try to classify these actuators or these micro actuators, they can be classified under three different categories. One, we call it as a non-contact actuator. The other one, we call it as a solid state actuator. Third one, we call it as a stepper actuator. So as far as these non-contact actuators are concerned, so these electromagnetic or electrostatic structures are considered to be a kind of a non-contact actuators. This is because the input energy is produced by the work resulting from the presence of the force. Now when we try to talk about a solid state actuator, the solid state actuator includes a thermal bimorph and a smart material such as shape memory alloys and piezoelectric actuators. The work is produced through stress variation resulting from change of material states. Similarly, when we try to talk about a stepper actuator, so in the case of a stepper actuator, we basically include the stick slip actuator. Then we have the impact drives. We also have the scratch drive based actuator. Basically, as far as in these actuators are concerned, the work is produced incrementally. Whereas in the case of a solid state actuator is concerned, we have the SMA and the piezoelectric actuator. So like we have talked about this bimorphs, etc. In fact, that also we will be discussing it in detail. So as far as the solid state actuators are concerned, the work is produced through stress variations resulting from a change of a material state. In the case of a non-contact based actuator, we have an electromagnetic actuator and the electrostatic actuator. And actuator. Okay, so as far as in this amplification of motion is concerned, in many cases the actuator motion ranges and or resolution do not match the desired range of motion of the mechanism output. So the interface mechanism to scale up or down the motion range of the actuator are needed to be the part of the mechanism. So if this is particularly like in the case of a solid state actuator. So in all these configurations, so wherever we require an amplification, so appropriately we can amplify these structures based on the functionalities. So as far as these amplification of motion is concerned, or amplification of these actuators are concerned, like structurally we are trying to modulate these micro actuators so that we can have an appropriate amplification in the actuation. So with reference to amplification perspective point of view, we can amplification these motions into three types. One is called as a bimorph assembly. The other one is called as an in-plane motion amplification. This in-plane motion amplification is further classified into three types. One is called as the lever mechanism type. The other one is called as the two-bar system. Which basically focuses on the up and down mechanism, and the third one is called as a push-pull assembly mechanism. Okay, so when we try to look into the bimorph assembly perspective point of view, so these bimorph assemblies, so as discussed earlier with reference to this shape memory lie perspective point of view also, so it has two different layers. So in the case of this bimorph, it consists of a kind of a sandwich structure of two or more different material with an asymmetric strain response to a common stimulus. So one of the sandwich structure can be a smart material, and the other one it itself can act as an actuator. So as in the case of bimetals. So these structures will have a different boundary between them. So like in fact in our case with reference to this bimorph assembly perspective point of view, so we have seen a bimorph assembly where so we have two medium. This is material 1 and this is material 2. So the actuation happens in such a way that so this material 1 and material 2 will move along the structures. So the two material with difference response is to give a stimulus for a continuous interface, and when we try to look into the asymmetric strain perspective point of view, these asymmetric strain response to a stimulus, either it might be a kind of a thermal or it might be a kind of an electric or a magnetic field. This will cause the assembly to bend on the sandwich material and do not expand on the same rate. So this mechanism forms an efficient propulsion mechanism So in fact, like this, although it's a kind of an in-plane bimorph, is conceptually possible at the design level. It remains very difficult and it is not possible to fabricate in a very small dimension. Therefore, most of these bimorphs are kind of a micro scale, which lead to a kind of a outplane motion amplification. Now, in the similar fashion, when we try to look into the lever mechanism perspective point of view, this is a kind of a lever mechanism. So if we look into the overall configuration, so the configuration looks something like this, where we will be having a kind of a solid state actuator. Two joints are there. And this is the kind of a solid state actuator. So here we have the joints in place, and this is a kind of an amplification. So this is the kind of a solid state actuator. And then we have two joints are there with the levers. Okay. So this is the kind of the structure where the solid state actuator is represented over here, and then we have a kind of a kinematic standpoint. This is called as a kinematic standpoint, and this is called as the one axis translation. So this as far as in this arrangement is concerned, so this is called as a lever amplification mechanism. Like in this lever amplification mechanism, it is based on the 4-bar mechanism. So from the viewpoint of kinematics in this design, the actuator can be seen as one of the one axis degrees of freedom, and it is almost equivalent to a prismatic joint. So the lever amplification is realized by using a pivot joint. A lever pivot around a point anchored to a fixed body. So two pivots are used to interface the linear motion of the actuator with the angular motion of the pivot. So the actuators forming the input of the mechanism are attached at one end, while the output of the mechanism can be any point on the lever. So the output point can be taken so that the displacement amplitude from the actuator is either amplified or reduced. So the scaling ratio between the input and the output is simply the relationship between the distance between the input and the lever pivot over the distance between the output. Okay, so like here in this particular case, so this is one arrangement. So we can also have one more arrangement. So here, so in this arrangement, it can be something like this. This is the solid state actuator. I can draw over here. We have a kind of a mechanism. This moves back and forth. So this is the solid state actuator, and here we can see an amplification which exhibits over here. So this is a kind of a translation which exhibits. So it is noted that like to convert this into a linear motion, it requires a kind of a linear guidance. if the arm is too long enough and the displacement is still small, the circular end effector motion can be neglected in the first approximation. So like as far as in this particular case is concerned, so it's a kind of a kinematic of a bar with two pivots which it can be used to accommodate the linear motion produced by the linear guidance of the system with the angular motion of the lever. Now let us see the next category, so which is called as a two-bar system. So as far as in this two-bar system is concerned, so in this two-bar system, this is connected something like this, and the overall theta is governed with this mechanism, and this is the actuator. Now, so it's a kind of a double beam motion amplification where various implementation exists based on the principle. So this is based on the length of the base of the triangle. Now, as far as in this two-bar system is concerned, so it consists of a symmetric triangular assembly with two arms of equal length. The actuator forms the basis of the triangle. When the length varies, it induces a displacement in the perpendicular direction. So whether the motion is in the perpendicular direction, it is amplified, or on the contrary reduced. So the motion amplified is in the function of the angle, which is nothing but the theta, and therefore the ratio between the length is appropriately adjusted. So this is one mechanism which we call it as a two-bar system mechanism. So like it has its own nitty-gritties, and appropriately when you try to deploy it in a field perspective point of view, it gets adjusted. So ideally wherever you want to have a kind of a linear amplification to a theta amplification, to a rotary amplification, we can deploy this particular mechanism. The other one mechanism which is available, which we call it as a push-pull mechanism or a push-pull assembly. So as far as in this push-pull assembly is concerned, the configuration looks something like this. Where we have a solid state actuator, okay, so this is a kind of a push-pull assembly. In fact, you can also have such kind of configuration, this kind of configuration also. So in this configuration, this is a kind of a translation which exhibits, and this is the, let us consider this as solid state actuator A1 and the solid state actuator A2. Okay, and this is an arrangement which is available. So like this is a kind of a combination which is used for a kind of a push-pull configuration. So in this configuration, we have two actuators which are mounted, so that when one shrinks, the other one elongates. The amplification is gain provided by the lever with a pivot. So the push-pull configurations can be adapted to any configurations, so that these two actuators can move and the same amount in the same direction. So based on the requirement, appropriately we can manipulate the moment in both the directions. Okay, so these are some of the different amplification mechanisms which are available, which caters the micro actuators related, which gets integrated with the micro actuators based on the different functionality. Of course, when we are trying to look into the biomimicking perspective point of view, so we will be going through much more amplifications which are being directly deployed in the field. So those are slightly different. Almost it has the similar mechanisms, but it will be a kind of an upgraded configurations which we will be discussing it as and when once we come to that module.